Hello everyone, my name is Yuta Morisawa from KDDI Research. Today, I'm talking about stream processing platform that achieves resource efficiency. Stream processing has become a major region. By 2025, nearly 30% of the data will be real-time, and it is common to run hundreds of stream applications in one organization because of business divergence and complexity. In such an environment, improvement of resource efficiency has become a critical challenge because low resource utilization leads directly to an increase in platform cost. However, traditional big data stream processing platforms are not resource efficient. The main reason is that users must allocate resources according to traffic peak. This graph shows an example of CPU usage of the stream processing. Sometimes the CPU is in underutilized state because input data rate often varies in time. In spite of this fact, once users create a cluster, the total amount of resources cannot be modified in current platforms. Motivated these facts, our research goal is to improve resource efficiency in an environment where multiple applications with different latency requirements exist. But improving resource efficiency is difficult. The first reason is that applications have different latency requirements. If there are many applications, SLA may vary drastically, but we need to meet every SLA. The second reason is unexpected traffic patterns. Input data rate often varies suddenly. Sometimes users must allocate extra resources to cope with it. The third reason is relevant to optimization. Improving the resource efficiency of every cluster is needed to minimize the platform cost. But existing studies on stream processing assumed that the cluster accommodated single application, and the effectiveness was limited in an environment where there are multiple applications. As for the data center optimization, a lot of studies have been made, such as data center OS, but these studies focused on batch computing. We couldn't adapt them to stream processing because the requirements are totally different. Particularly, stream processing requires significant low latency. We developed a new platform that achieved resource-efficient stream processing. There are two key features. First point is to accommodate multiple applications in one Spark application. That means applications share resources. If one application needs more resources, the other applications can give them, and vice versa. We adapted the design because it achieved the finest granularity of resource management. Another reason is that reallocating processes can be completed with lower latency. This design allows the master process to monitor every application and manipulate its scheduling order. This feature is desirable for stream applications because they are latency sensitive. Second point is task-level scheduling with latency-aware algorithms. Most of the stream applications have requirements on latency, but the default schedulers in Spark do not consider latency, even though the goals of the platforms should be for records to be processed in less time than the request latency. So we developed latency-aware schedulers that determine the execution order of each application to observe application's latency SLAs. This figure shows the architecture overview. We implemented the platform based on Apache Spark. Left side box named the Spark driver is a master process, and right side box is named executor or worker processes. In master process, applications are assigned to dedicated scheduling pools and scheduled in task level granularity. Executors just runs assigned tasks and they do not care what the applications are. We do not allow applications to read other applications' data because if permitted, the scheduler must consider the dependency between applications, which makes algorithms complex. The platform is fully API compatible with Apache Spark because we didn't made any change except schedulers. Next, I'll talk about schedule design. We had two design choices, white box and black box. White box means estimating the necessary resources before execution. This design is suitable for batch computing because we can know the amount of data, the number of available cores, and so on precisely. However, it is difficult to apply to stream applications because data rate varies in time. So we chose black box design. Black box means using only measurable metrics such as latency. The master process monitors the latency and manipulates resource allocation. How black box design works. We utilize existing Spark scheduler. First of all, Spark has two scheduling layers, job level and task level. The job is a unit of execution composed of tasks, and the task is an atomic unit of execution. The task level layer is able to do more fine-grained scheduling. So we implemented our algorithms based on the task level scheduling mechanism. Resource allocation is done by three steps. First, resource offer is issued by executor. The resource offer is a message that tells master some resources are now available. Second, task scheduler calculates priorities of each pool. And last, the scheduler allocates resources according to the priorities. Unlike the default schedulers that statically determine the priority of the pools, our scheduler calculates priority for each resource offer that comes in, and then allocates resources dynamically. Here we will present how the scheduler determines the task priority. We implemented three algorithms: earliest, deadline first, EDF, priority-based EDF, and process time estimation. Earliest deadline first simply uses the remaining time as a criterion. Now, when we define TS as a job submission time, TC as a current time, LS as a latency SLA, the remaining time is shown as TS plus LS minus TC. We define the priority PS as the opposite value of it. The scheduler calculates PS for each job of each application, and then find the biggest PS in each pool of the representative value. Finally, resources are allocated in order of the pool with the largest representative value. It means the pool which we have the biggest representative value obtains resources first. A resource allocation unit is task set, which is a group of tasks and is a component of the job. Tasks in the task set are scheduled at the same time. Priority-based EDF is a modified version of EDF. We added the potential priority of the applications. For example, anomaly detection may have higher priority than aggregation for visualization. The equation is modified like this. We multiply the PS by the potential priority. The last one is process time estimation. We added estimated job execution time. F is an estimation function, and I is the input data rate. In this paper, F is defined through the measurement of actual latency. In the end, we subtracted the predicted time from the remaining time in the equation. For evaluation, we prepared Hadoop cluster with 5 servers. Specifications are shown in the right table. We use the 3 types of connected applications for evaluation: parsing, searching, and windowing. Parsing. It parses the binary input data for conversion into the data frame format. Searching. It searches a target to report, for example, road warnings, by calculating the distance between a specific landmark and each car. Windowing. It counted the number of cars in the targeted areas with a sliding window for statistics. We compared with the proposed platform with 3 latency-aware schedulers and default Spark. These graphs show the results. First, we evaluated how much resources are saved. For the experiment, we adjusted the number of CPU cores and investigated the minimum numbers needed to maintain the latency SLA. We also adjusted the memory size, but it didn't affect the result. The left graph shows the required minimum number of CPU cores needed to observe applications SLA. Default Spark runs applications separately, and the result is shown as separating. The default needs 39 CPU cores in total to observe latency SLAs. On the other hand, the proposal needs only 25 cores. It means the proposed platform with latency-aware scheduler achieved the same performance with only 64% of CPU cores. The right graph shows the CPU time during experiment. Except for separating, the platform collocated applications in one cluster and used a corresponding scheduling algorithm. The graph showed that by collocating applications, the platform achieved twice as much CPU utilization than separating. That means in separating, CPU spent more and utilized the time due to input data rate variation. Next, we compare the scheduling algorithms. The left graph shows the normalized latency for each application type and each scheduling method. The latency is normalized by the latency of the default Spark. I note that the number of CPU cores in the cluster was 25, and the default Spark used 39 cores in total. So if the value is smaller than 1, it means that the platform achieved a smaller latency with fewer resources than the default. The legends EDF, PT, and EST are the proposed methods. FAIR and FIFO are the default scheduling algorithms. The graph shows that PT, priority-based EDF, achieved both min and max are less than 1 in every application type. The reason is that it allocates resources based on the latency metrics. FIFO and FAIR do not consider latency, so they allocated a surplus resources to windowing, even though the latency of windowing fully satisfied the SLA. Finally, we overloaded the platform. The right graph shows the number of records violated latency SLAs. The key point of the graph is that EDF, one of the proposed methods, achieved to reduce SLA violation significantly. The difference is more than 1,000 times compared to FIFO. Let me conclude the presentation. Our goal is to create resource-efficient stream processing. We propose a platform that accommodates multiple applications and latency-aware schedulers. As for future work, isolation is a major trade-off with resource efficiency. Our platform did not provide an isolated environment for each application. So if an application fell into infinite loops, it causes some effects on the performance of other applications. And the current version of our platform, the scheduler considers only CPU cores as resources. We needed to consider other resources such as memory. Thank you. If you have any questions, please feel free to contact us.